Hey guys, what is up? Welcome back to your next course in Low Level Academy. Today we're going to start the networking code that doesn't suck course. So we're going to go from the fundamentals of C, which you learned in the previous course, Zero to Hero C programming. And again, if you haven't taken that course, if you haven't finished that course, please go and finish that course because this one will depend heavily on that one. We're going to take the foundations that you learned in C and then apply the C socket library on top of that information and take the project that we built, our employee database, and turn it into a fully fledged networking application. We'll get a little more into the details of that in lesson 3 where we talk about the project itself. But this course is going to be meant for somebody that may not necessarily know networking at all, may not know how the internet works. In the first section of this course, we'll talk about how the internet works at a high level and how that matters for programmers. In the next section after that, we'll talk about C networking fundamentals, so how to use the POSIX Socket API to make connections between programs and exchange data. We'll talk about some advanced data marshaling topics, things that you can do like Google's protobuf, for example, to serialize data in a way that isn't custom to reduce your attack surface for bugs. And then after that, the final section will be taking our employee database from the previous course and then turning that into a networked appliance. So I'm really happy you're here. We'll see you guys in the next lesson where we talk about the tool setup and environment setup for this course. Let's get after it. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck here on Low Level Academy. Today, very quick lesson. It's going to talk about the tool setup and the environment setup for our project. So again, if you're taking this course, you likely have already taken the previous course, Zero to Hero C programming, and the environment setup is exactly the same, no major changes. If you have forgotten or it's been a minute, all you need to do is be in a Linux environment. So uname-tac A tells me that I am in Ubuntu 2004 LTS. And then you also have to have the GNU toolchain GCC installed. I have it installed here. If you don't have it installed for some reason, you're making maybe a new setup. Sudo apt install GCC, and then I already have it installed, but this will populate it for you. And then by installing GCC, you also install all the libraries and environment that you need to compile C code as well. So all the headers we'll be using in our code to use the socket library and stuff like that. So you have GCC, you have a Linux environment, and also next you're just going to want to use your favorite editor, your favorite text editor. I'd like to use Vim. Vim has a bunch of cool features you can use to make your project a little easier to sort through. I use NeoVim using NVChad. Not everyone likes Vim. I find it also a little simpler. Maybe people that are newer to programming want to use something like gedit, the basic built-in editor that comes with Ubuntu. Will edit source parse.c, right? Very straightforward white text editor here. You get to use your mouse, whereas Vim is a lot more motion-based and keyboard-based. So break out your text editor that you're comfortable with, break out your GCC and your Linux environment, and move on to the next lesson where we talk about what we're going to be doing with the project. And then after that, we'll talk about the fundamentals of networking as applied to this course. So we'll see you guys there. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck today on Low Level Academy. Today I'm going to talk about what the project we'll be doing at the end of this course will be and kind of the mindset you should have in doing this course, right? So just like the previous course, while you're taking this course, take the fundamentals, learn them separately, but while you're learning them, try to figure out how you can apply them to the final project. And then in the final section, take the fundamentals and then apply them, right? So learn the basics and then apply them in the end. What we're going to do today is kind of walk through, as a reminder, maybe you took this course a long time ago, what we built in the first course, right? And again, I'm not going to provide source code for this project because I highly recommend you go and build it yourself, because if you don't, you're going to miss out on all of the C fundamentals that will bite you when you're learning the fundamentals of sockets in C. Okay. So in the final project, what we did is we built the program dbView, and it had a couple options here. I'm missing the two additional arguments, list and add. But using the dbView program that we wrote, it's going to be able to open and parse our database file that contains all of our employees, right? And then we can take some action on that database. We can list the employees, and here that I see that I have employee 0. His name is Timmy H. He lives at 123 Cheshire Lane, and he worked 120 hours this month. This is a cool program, but it doesn't do a lot for somebody outside of my computer, right? If I have this program, if I wanted someone to also be able to parse this database, I would have to send them the program, also send them the database, have them perform some kind of action on it, and then send it back to me. That sucks. So what we're going to do instead is we are going to edit the source code of this program to make this a network appliance, right? So what will happen is dbView will become dbServer. We will open a database file and we'll allow connections from a client program that we're going to write, where the client program will be able to authenticate to our server. We'll set some kind of secret password, secret username, and then they can add, remove, and list employees over the network using a custom protocol that we implement, right? That'll be the course project that we do. So as you're going through the future lessons, figure out how the things I'm teaching you can apply to that. Also, just like in Zero to Hero C programming, please, as you're learning these topics, learn them slowly. Take them in, take the code that I give you in the course, in the lessons, and break them down, write them yourself, make modifications to it, see if you can break it. If you break it, figure out why it breaks. You really have to internalize information before you can apply it to a project. Otherwise, you're just going to start guessing and you're going to get very overwhelmed. So take your time with this course. Don't rush through it. I would say do 1, maybe 2 modules a week at most. So anyway, that is the project for this course. That will end the introduction section of this course. I'll move on to module 2, where we talk about the fundamentals of networking at a very high level as it applies to network programming. So we'll see you in the next one. See you there. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. Now I know this is a C programming course. You're probably curious why there is a network diagram on the board here, but I think it's very important for people that want to do networking code to understand how networks work, right? That seems pretty straightforward. So today we're talking at a very high level about how the internet works. Now I know that sounds like a lot of information, and it is. I mean, literally you could spend multiple months of your life just in a Cisco course learning about the details of how the internet works. So we're going to cover this at a very high level today to figure out exactly how this affects how we program, right? So we're going to talk about what happens when you go and you visit google.com, right? What specifically on the network happens and how does that play into our code? So when you put google.com into your browser, a couple things happen in the background where effectively the computer has to figure out what does the word Google mean, right? Eventually, through the course of DNS, which is domain name service, you can go Google how that works in the background. It's a little more, it's a different course than this course. It converts the word google.com into an IP address. IP address is just literally a number that represents a computer on the internet. There are different kinds of IP addresses. There are public and private IP addresses. For the sake of this course, we'll keep it simple and just talk about private IP addresses. The 10 series of IP addresses is a Class C private IP address that you can't use publicly on the internet. But let's pretend, for example, that through DNS, our google.com actually resulted in 10.0.1.1. So this is the address of google.com. We've converted google.com, the DNS record, into a physical number. So we said we're putting it into our browser, right? So this is the address of google.com. We need both an IP address and a port number. So if you think of the computer as a shipping yard, right? Like, you know, your local port where your country or whatever receives goods and services from other countries around the world, that is going to be the port that things can actually come in to your computer, right? So if you consider that this is the IP address, the location of the port, the specific slot that's carved out for your information is the port number. So for HTTP, which is the protocol that your browser uses to exchange information with a server, that port is port number 80. So what your computer is going to do is actually going to craft a packet locally. We'll make a little square here to denote your packet that will contain the request of information that it wants to ask google.com. And HTTP, again, is its entire own spec. We'll worry about that later in a future lesson. But what's going to happen is it's going to form a packet where the source address is going to be this address here. It's going to say that it came from us, 10.0.0.1, and the destination address is going to be 10.0.1.1, the destination of Google. It's also going to have a source port, which is going to be some random number on the computer. Don't worry about that. But the destination port will be port 80. Once we have that packet created, the computer will put it on the wire and send it out to its local gateway, which the local gateway has a very specific function. Local gateway's job is to take a packet that it receives and based on the destination IP address, look up in its routing table how to get to that IP address. And the routing table here, because we only have one connection, will tell us the only hop available is to go to this next hop. And that process goes and goes and goes until the packet is finally emitted out of this wire into the switch, and the switch sends it to google.com, and thus an established connection is created where now the computers are able to talk over this path that the computers have created via these routers. Now, I know that is a very gross simplification of how the internet works at a high level, but what we're going to be doing in this course is writing a server client system. So to do that, we had to know kind of the basics of IP addressing and ports, right? So what we're going to do is make a service that binds to port 5555. We are going to write the server software. Think of us as the Google, but we're also going to write the client software. And what we'll be able to do is in the client software, specify an IP address to connect to, and that IP address will be something like 10.0.1.1, and we'll connect to it on port 5555, and then exchange the information via the protocol that we come up with. So that is how the internet works at like a very high level, how data exchange works, what an IP address is, and what a port is. That's it for now. We'll see you guys in the next lesson where we talk about TCP and UDP, which are two different kinds of network layers that affect how data is sent between two computers. We'll talk about that in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck here on Low Level Academy. Today we're talking about a very fundamental piece of information as it applies to network programming, the differentiation between TCP and UDP. That is Transmission Control Protocol and User Datagram Protocol. The names aren't as important as the details beneath them. So to understand why this even matters, we kind of have to go a little deeper into how data is sent on the internet. I know in the previous lesson, I kind of made up this little blob, right? This was a little thing, little piece of data that we wanted to send to google.com that represented our HTTP request, right? So when we put HTTP, :google.com into the browser, I said that the computer created this little thing, and the thing had a destination IP address, it had a source IP address, it had a dest port, and it also had a source port, right? These are all the details that Google needs to know about, or the routers in between us need to know about to get that packet to the right person. And this is all true, right? And inside of this packet that we're going to have is going to have the GET request that tells Google, hey, I would like to get page index.html, right? All of this is true. But I did kind of overgloss a little nitty-gritty detail. So we have the IP address, right? The IP address, according to the OSI model, which is the model that represents the protocols of the internet, is a layer 3 protocol. IP is a layer 3 protocol. These other ones, the ports, are the next level above the IP address. Layer 3 is the network layer, and then layer 4 is the transport layer. Now, there is another protocol that rides on top of IP that contains the destination port and source port, and there are actually two of them, and as the name of the lesson implies, shocker, they're TCP and UDP. Now, when does each one get used, and what are kind of the pros and cons of TCP versus UDP, and even more importantly, what are we going to be using in our project? Well, let's talk about each one individually first. So TCP, or Transmission Control Protocol, is a protocol that has what is known as a lot more overhead going on with the protocol, right? TCP, the way that you initiate a TCP connection is before any data is actually sent between two devices. So let's say we have node A and node B, and we can pretend that A is us and B is google.com in this scenario. 3 packets actually have to get sent for an established connection to exist. So A will send a packet to B, and inside the TCP packet, there are these different flags that denote different parts of the TCP protocol. So A will send a SYN packet. This is just a flag in the TCP spec. Don't worry about the details right now. And if B is able to respond to this packet, if the port is open, if you didn't get blocked by any firewalls in the middle, B will respond with not only a SYN flag TCP packet, but also ACK. It means it acknowledges the SYN packet. And then A will respond again with the ACK packet, which means that it acknowledges B's acknowledgement. Once these 3 packets have been exchanged, both computers recognize a connection between A and B, which means they will freely accept data from one another as long as certain details within the TCP packet protocol are met. Don't worry about the details of that right now, but this is the fundamentals of TCP. And what's cool about TCP is that, for example, if if node A sent data to packet or to node B, right, and it was some big data, it was like A, it was a bunch of data. If for whatever reason some of this got clobbered, it got lost in translation, the TCP protocol is actually designed in a very specific way that B will tell A, hey man, I didn't get all of the information, can you resend it? And TCP will handle it internal to the kernel to resend the data for you. All of this will happen for you in the computer. UDP, which is the other protocol, is known more as kind of a fire and forget protocol. So let's talk about what that specifically means. UDP is called User Datagram Protocol. So remember again, we have computers A and computers B, right? Previously, we were talking about HTTP, and HTTP is happening over TCP port 80. So this would never happen over UDP. But let's say, for example, we wanted to talk to Google.com. We wanted to get a DNS request to happen on Google.com. We wanted to ask Google a DNS question. What is the IP address of Bing.com, for example? That happens on port 53 over UDP, right? A different layer 4 protocol. And UDP is different because there is no connection establishment via UDP. The idea of a connection in UDP is not a real thing. Basically, in UDP, you just kind of shout at the server, you say, blah, data, and then there's no receipt. You don't get a response if the program got the data via the UDP spec. You could add to your own custom protocol maybe a piece of information that B sends to A that says data check, right? It happens at the application layer, the layer that we're going to write. But specifically within UDP, there is no information that tells A that any of the data was received. And also, again, there's no concept of a connection. So UDP is meant for data services that are meant to be streamed and where packet loss is okay. So UDP is very common for voice services, video services, anything where you don't need to have all the information in total. You can lose parts of it in between. Whereas things like TCP are used for things like maybe file transfers, where you need to have all the data. You can't have any loss. And the TCP protocol actually handles loss at the network layer. So for our service, because we want to make sure that our employee database is not lost in translation, it is not a streamable piece of data, we are going to be using TCP on port 5555. I'll get my fat head out of the way. We'll do 5555, just like we talked about previously. So that is TCP versus UDP at a very high level. This will matter in the course because as we go into the actual programming, when you create a socket, which like I said before is an associated IP address in port on a computer, you have to tell the computer when you're programming it if it's a TCP or a UDP socket, because that changes where it binds on the computer. So for all intents and purposes, in this course, we'll be using TCP port 5555 to create our service. And we'll see you guys in the next lesson. Hope you learned something. Again, please slow down, internalize this, maybe read some articles that I link here in the course content, and we'll see you in the next one. If you have any questions, also go hit up the Discord, and we'll see you guys there. Bye-bye. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. Today we're talking about how computers talk, specifically what calls have to happen in C for two computers to establish a connection, and how does that have to do with the TCP network layer, right? Now, this is the final lesson that we are doing that does not involve coding. We will start coding in the next lesson. I just want to make sure that we have the fundamentals down so that the network layer itself does not confuse you before you get into the actual C programming, which will probably confuse you even more if you don't have the fundamentals, right? So when you have network code, you are fundamentally going to establish, like we said before, over TCP, a connection between two nodes. We have node A and node B. And we'll say that node A is the client. We'll call it a client. And we'll have the server. So it's going to be serverb, right? Server and client, right? So before anything is allowed to happen on the client, before the client can try to establish a connection, we have to bind a port on the server to listen for a client connection, right? We can't establish a connection if the server isn't openly listening to it, right? So the calls that we're going to make in C, and this we're going to go into the detail, obviously, of these in next lessons, are going to be the following calls. So the first call is going to be the socket call. What the socket call does in C, and please go consult the man page, go read the man page for details if you have questions, but these are the high-level fundamentals. The socket call creates a socket object or a socket file descriptor in C, which represents either a port or a connection in C that we're going to use to eventually listen for connections. So once the socket is created, we now have to bind that socket to a specific port. So we're going to have the socket come out of this. It'll return a file descriptor. And then we're going to call bind. Bind is going to bind that socket to a specific address and port. Remember that I said before that, connections are made between computers via addresses and ports. In the bind call, we are going to choose what address we bind to and what port we bind to. We're going to do another call called listen, which basically just sets up how many devices we can listen to. That one's not so important. But the final call that'll matter is going to be the accept call. Now, the accept call is going to be the call that puts the socket into a state where it's openly waiting for a connection to occur. The listen call is actually a misnomer. This doesn't wait for the connection. The accept call does. With the accept call open, what's happening is the call is going to block. It's not going to return until a connection is made from a client. So let's walk through what the client does. The socket is created for a client as well. This will represent a socket that can make a connection and eventually will represent the connection between the server, right? So the socket comes out. All of this does not happen on the client. All we do with the socket now is call connect. And what is the connect parameter going to take? Most likely it'll take an address and a port. Very good guess. And the address and the port will be the same as this address and port, right? It'll be the address of the server. And the connect is going to connect to the accept. Once that is done, the connect call actually initiates that TCP connection we're talking about, the SYN/SYNAC ACK. And once this has all happened, we now have an established TCP connection with two file descriptors. Let's talk about how we use those. So again, remember before we have the client and the server. On the client and the server, we have two file descriptors. FD, we're going to call them, right? These are our sockets. With our file descriptors created and the connection made, remember we have that TCP connection established via the connect and accept calls. We have TCP. Now we can treat the file descriptors like files. And what do we do with files? We write to files and we read from files. We are now able to use the socket file descriptor like it's intended as a file to transmit information back and forth between the servers. If I want to send hello world to the server, I literally call write on our file descriptor from the socket and it'll be read by the server. And inversely, if I want to write to the client a response when it says hello, I say, hey babe, right? I write that to my file descriptor that came out of accept, and then we get the same data that comes back from read. So now with the connection established, we can just treat the file descriptor as a file and data will get sent across our TCP established connection. So that is how computers talk at a very high level. Please go do some additional reading that I have resources here below, and get ready for the next lesson that'll happen next week where we talk about how to actually code this in C using these calls: socket, bind, listen, accept, connect. These are all the calls that we're going to use in this course, but the details of how we use them and kind of the edge cases are going to make them very, very specific. So we'll see you guys in the next modules. Get ready to write some awesome C code and to turn our database project into a networked appliance. I'll see you in the next lessons. Take care. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. The first lesson that we're going to actually write a little bit of C code. So in this lesson, we're going to be creating C code that creates a socket, and this code will translate for both our server and our client that we're going to write in this course. What is a socket? So we described this before in the previous lesson, where a socket is basically just a file descriptor. Everything in Unix can be treated as a file, and the number that represents that file is a file descriptor. Now, we learned this in the previous course, 0 to Hero C Programming, where we were able to open our file that contained our database, and we got back a number, right? That file descriptor that internal to the kernel, as it associates to our process, was the number that represented our open file that we're able to write data to and from, right? When we create sockets, and sockets are being used for network programming, we also get back file descriptors. So if I made a file descriptor and I opened the local file, like if I opened my database again, right? This file descriptor would probably be file descriptor 3 because we already have standard in, out, and error open. So now the third one is open. Now, if instead of doing this, I call the socket function, this will also return the number 3. Both are treated as files in C. So what is a socket? A socket, as it's described here, is just an endpoint for communication. Now in Unix, sockets have a bunch of different functionality. There are Unix sockets, there are domain sockets. There's a ton of different options you have when you're using sockets in C. For the purposes of this course, we are just going to be using one type of C socket, one type of Unix socket, and it's going to be a IPv4 TCP socket. So to create a socket in C, we have to call the socket function. And as any function that we use in C that is coming from glibc, the main library that comes with our programs, I'm going to be using the man page, right? So like all I typed was man socket, and boom, we get a very healthy description of what's happening in our code. So we can first take this code here, because we always have to steal the header files when we're using outside functions. Very good, we have those. And now we can actually call the socket function. So the question is, what are the parameters of the socket function? Socket function takes a domain, a type, and a protocol. So the domain is basically describing what is the layer 3 protocol that's happening in our socket. So for this one, we're going to be using just AF-INET, which describes that we're going to be using IPv4 internet protocols, right? We're just going to have layer 3 be basic IPv4. So the socket's first parameter is going to be AF-INET. And then after that, we have to put the protocol that or the type that we're using, and the type is going to be a sock stream. So like I said before, we have the option to use either TCP or UDP in this project. We are going to use UDP. If, for example, in maybe your personal research, you wanted to make a UDP socket, you would choose socket dgram for datagram, which is the D in UDP. It's a datagram. And again, it says here supports datagrams, which are connectionless, unreliable messages of a fixed maximum length, whereas a socket stream provides sequenced, reliable, two-way connection-based byte streams, which is describing TCP. So we'll take socket stream here, and we'll put this into our socket. And then finally, we will specify the protocol. And basically, all the protocol man page says is basically if there is no specific value you need to put in for protocol, like because we're just doing basic INET TCP, we can just put 0 in the protocol section here. So cool, we call socket, and just like any function that we call, we always check the return value. So what is a bad return value from the socket function? -1 is returned if the program fails and error no is set. So what we can do is we can say if fd is equal to -1, do p error on socket, which prints the error number description, and then we will simply return. And then actually we'll return -1 because this is main. And then we'll also, just to show you what the socket actually is, we're going to print our socket like that. Very good. So we print FD, and that should just be the number 3. So let's get out of here and go print that real quick. Socket on socket, and it's number 3. Very simple. So you're probably thinking, what does this do for us? Well, this file descriptor now represents an endpoint for connection that can be used to do either client-side communication or server-side communication. So using this file descriptor, I can pass this into the future function calls in the server of bind, listen, accept, or I can pass this into the function connect on the client side to connect to that bound server. So we're going to take this code and use it in both our client and our server in the next 2 lessons, and use this to connect to each other and exchange data over the internet. So let's take this code, move on to the next lesson where we build our simple server. I'll see you guys there. Take care. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. This one will be a little longer today. We're actually going to take this code that we have here from our previous lesson to create a socket, and we're going to expand it all the way to where we have a basic server running, right? The server is going to bind to a port, we'll call it port 5555, and then we're going to listen for a connection from our client that we'll write in the next lesson. So to do a server in C, like I said before, the function calls are always the same because you're always doing the same process. You have to bind to a port using your socket. You have to set the backlog using listen to be some number of backlogged connections. And then finally, you have to use accept to accept the connection from a client, right? So what we're going to do is we're going to just run a couple man commands. We're going to do man bind to first figure out what we have to do to run bind. So we already have these included here. The bind function, all it does is it binds a name to a socket, and the name here is meaning the name of the computer and the port. So it's going to be the IP address and the port number. We have a couple new structures popping up here. We have sockadder and socklent. So we pass in our FD, but we also have to pass in some information about what we specifically want to bind to. And to do that, we actually are going to use not the sockadder structure, but the sock adder in structure. Now the sock adder in structure is the same as the sock adder structure, but what it does is it has named fields that we can use to fill in and put in the information we want, and then we just cast it to a sock adder before we call bind. So we're going to say struct sock adder in, and again, this is a socket address information structure. So we're going to call it server info because this just contains information about the server that we're going to bind to. And then we always want to use this notation here to zero out our server info sock adder structure. Because if we don't, if we set some of these fields to erroneous values, it may cause bind to fail, and we don't want that. Now, to use the server info structure, there are some fields. The first one is called sin family or socket in family. We have to tell the server info structure what socket type we're using. And again, this is what socket family we're using. And again, this is an AF INET family. The AF INET family meaning it's an IPv4 structure, an IPv4 socket. Next, we want to tell it what address we want to bind to. So this is sinadder.sadder, and we're going to tell it what address are we going to listen for connections on. Like I said before, if there is going to be a destination IP address on the client's packet that gets to us, we have to make sure that we're actually listening to an IP address that we're allowed to receive connections from. Now, what we actually can just do is set this to 0. By setting it to 0, we actually bind to every IP address that our computer owns, which means that we'll listen to localhost, we listen to our named IP addresses like 10.0.0.1. We will be able to accept connections from every IP address that comes to us. And then finally, we have to set the port number, right? Because we have the IP address, but no connection is complete without a good port number. So we'll say that serverinfo.sin port is equal to 5555. Now there is a little bit of an error here. Maybe if you already coded some C code, you see it. But when we are doing network programming, there becomes an issue of endianness. Now, endianness is this idea of how computers store numbers that are bigger than one word size. So for example, the Intel processor is a little endian processor. So 1, 2, 3, 4, 5, 6, 7, right? Let's say, for example, is our number, 7, 8. Because this number is multiple characters, there's a question of what numbers go into memory first. Do the littlest pieces go into memory first, or do the biggest pieces go into memory first? Intel is a little endian system, which means that technically 7, 8 would go into memory before 5, 6, before 3, 4, before 1, 2, and so on. A big endian system in memory, the number would actually look like the opposite. It would look like 7, 8, 5, 6, 3, 4, 1, 2. It would be completely backwards. The way that in network code we handle this is we convert all numbers to what is called network endianness, or it's called network endian, which is big endian. The way we do this is we say host to network, H2N, and then the size of the data. And because port numbers are only 2 bytes long, we do short. So host to network short on this number. And this is going to be the case for any data that we send across the network. If it is a packeted piece of information, we have to convert it to network endianness. So we now have the family, the address, and the port all set up. Now we can do our call to bind. So how do we do this? We first put in bind, and we have to say the file descriptor we're going to bind with, and then the address of our server info. But because this expects a struct sock adder and not a sock adder in, all we have to do is cast this to the proper type. So we're going to do a typecast by saying struct sock adder star, and then do the address of server info. Again, we are required to put in a pointer to that information. We get a pointer by doing the ampersand, and we cast that pointer to the proper type. And then finally, it wants to know how big our information is. The size of this matters because it changes what kind of socket we have. If it's bigger, it could be IPv6. So we just have to specify the size of server info to get the information. We're going to say if this is, we have to check it. Like any good function that we call in C, we have to check to make sure that it didn't fail, and we'll check the return value. So on success, 0 is returned. On error, -1 is returned. So if this is double equal to -1, we will say p error bind, And then we have to also close our FD because we already have a socket open, and then we'll return -1. So if we failed to bind, we'll say why we failed to bind, and then we'll close the FD and move on with our lives. Very good. So let's compile this and see if it actually binds. So we could do gcc tac o socket.c. Very good. Aha, so a couple errors here. I need to provide the header that specifies the sock adder in information. And that's going to be net inet in.h. And also don't forget to add ARPA inet so that you get access to the H2 network short functions. If you don't, you'll get a compiler warning. So we add these two things here. And now in theory, what's happening is that we have bound our socket to a specific port and address. So let's do this. It's fine, but don't worry about that right now. So you won't be able to see anything happening if we do socket. So a way that I check to see what's happening with my system calls, and yes, all of these are just wrappers for system calls, we can run strace on our program, and you will see that the socket function is being called. We are getting 3 in return, and then bind is being called, and we're getting 0, which is a good function, which is a good return value. So this means that our function is happening and returning successfully, so we can move on and write code another day. So next we're gonna move on to the listen call. So man listen, very good. So listen takes a socket file descriptor, so we're a file descriptor for our server, and then a backlog, which just means the amount of the maximum length that our queue can be for connections that haven't been processed yet. So we're just gonna put 0 into this to make it an infinite backlog. Don't worry too much about this. And then also the return value here is also -1. So we could just say if listen on FD of 0 is equal to -1, p error on listen, and then close the FD, and then return -1. Very good. I have literally never seen listen fail in my entire life, but we're just going to check it real quick just to make sense. So we'll do this, we'll do strace, and then listen also passes. Very good. Okay, and then finally, the most important and the most interesting one, accept. So like I said before, accept, all it does is it blocks the program's execution, and it waits for a connection to be taken in. And when it does, it returns a new file descriptor that represents the connection between your computer and that computer, right? So we're going to figure out how accept works by running man accept. So what accept does is it actually takes in the same parameters as bind, but instead of reading from them to get information about them, accept actually writes to them to tell you where the connection came from. So you get an FD out of this, and you can also get the socket adder information out of them as well. So we have to make 2 new structures. We have to say struct sock adder in client info. This will contain information about the client is equal to 0. We also have to say int client size equals 0, because we have to write the client size as well. Just like we took it in the bind call, we have to also give it out in the accept call. So we'll say int client FD, a new file descriptor that represents our connection with the client, is equal to accept from our current socket file descriptor or server file descriptor to same thing as before, only now it's the address of client info and the address of client size. And go like this. And if CFD is equal to -1, we'll p error on accept. We will close FD, return -1. And then at the end of all this, we can close CFD. We will close the client as well. So we'll accept a connection and immediately close it. Okay, cool. So we have all this code written. We can do GCC on this, same error as before. So let's strace our program and see what's happening. Aha, so we have some new functionality here. So we have the socket being created that represents an IP over TCP, a TCP IP connection. We're binding that port to all of the addresses, IP address 0000 on port 5555, and it's passing. We're listening for an unlimited amount of backlogged connections, and then accept is blocking. It's not running right now. And why is that happening? The system call is waiting for us to connect to the server. Very interesting. So from a different tab, we can connect to ourselves locally on that port, and we can watch that accept will actually accept the connection and then close it. So we can do netcat to localhost, which is one of the addresses that I'm bound to on this computer, and I can do 5555. We'll see that we got a connection, which is what's happening here. It returns the socket file descriptor 4, and then we close 4, and then we exit. Now, Netcat's a little confused because that's kind of weird that it happened like this, but we did connect, and we could have sent data to Netcat. So that is our server at a very high level. We will use this exact same code in our project to kind of create boilerplate code to just give us a socket file descriptor that's bound and then exchange data over it. So in the next lesson, we create the client in C that will also talk to a server on port 5555. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. So as a little refresher, in our previous lesson, we took the basic system calls that we had to use to write a server out in C, and we made a server, right? So we created our socket, we bound to that socket's port, we bound that socket to a port, we set it up to be a passive socket to listen for connections, and then we listened for a connection with accept, and when accept returns, it returns a new file descriptor that represents a new socket that represents the connection to that client. And then very simply, after that connection is made, we immediately close it. So that's how the server works. So we are going today in this video write our client, and the client is going to be a lot of the same code, not so much for this area, but creating the actual socket itself. We are going to have to create server info that represents the server we want to connect to. So a lot of the same code here. And then so we'll use that. And then we'll eventually call the connect command that will connect to a socket given an address and a port that is listening via accept. And if they link up and the port is open, then we'll get a connection and we can do additional stuff in a future lesson. So because so much of this code is the same, I have my server.c here. We're just going to copy it. We'll call it client.c. So copy from server.c to client.c. And then we're going to vim client.c. You'll see I'm also in tmux in this session. I'll talk about the keystrokes I'm using when I'm going through the later part of this lesson. But tmux effectively is a way that you can have multiple windows in the same terminal session. It makes doing multiple tasks a lot easier if you're not using an already tiling window manager like i3, for example. So we have our client.c here. There are some things we do need to change. So first of all, we can delete client info and client size because we don't have a client that's going to connect to us. We are the client. The server info is still going to represent the information that we want to convey about what server we're connecting to. So the family of the server is still an AF-INET, that means IPv4, and the port is still port 5555, right? Because the types and the ports have to be the same. What has to change here is we have to actually specify what IP address we'd like to connect to. Because again, remember before, in our server, we just bound to all addresses that our computer was able to bind to. Here, we need to specify to the router ahead of us or the routers along the way, hey, what IP address are we trying to get to? So the way that we can actually do this, we can use the command inetadder, which will take a string as input, right, to the command, and it'll output, and we're going to look at the man page here to kind of show what we're doing, an inaddr_t, which is exactly the type of structure that an sadder is, right? It is an inaddr_t. So we're going to do inetadder, and I could specify, 120007 or 127001 or something like that. But we're going to make our program dynamic, and we're going to allow it to take an argument from the command line as input, which you learned in 0 to Hero C programming is done via argv. So first of all, we have to actually add that to our prototype. So we'll do int argc and then char array pointer argv. We'll also validate if argc does not equal to, meaning we did not specify a IP address. We'll say print. The usage of this program is to print the name of the program, which is argv1, and then the IP address of the host, right? Something like that. And we'll say argv0 here, bada bing, and then we'll return 0 to kind of show that the program has ended with no good cause. So if we do this, we'll get inetargv, we'll get inetadder to output the conversion of a string, which is this input, to an inaddr_t type, right? Because what we can't do is put in the string here, because this is not a proper IP address type. Remember, an IP address is just 4 numbers put together. So we have to convert that to the actual IP address value, which is what inetadder does. Very cool. So the socket stays the same because it's still an AF-INET or IPv4 socket. It's still TCP. What we're not going to do is we're not going to bind, we're not going to listen, we're not going to accept. So we can delete all of this stuff. So once the socket has been created, all we have to do is run the connect function, which takes the socket that we have, our client socket, and connects out to a server info. And again, just to verify this, you're always checking your man pages. Let's read connect. So it takes a socket FD, our socket, the adder pointer, and then the address length, which is the size of the value. So we'll do cast this to a struct sock adder, not stuck, struct sock adder pointer, the address of server info, and also we'll do the size of server info like this. And then we'll, as usual, check for the return value of connect, which is found here. So if the connection is successful, 0 is returned, otherwise it returns -1. So if connect is equal to -1, we'll p error on connect, what went wrong, and then we'll return 0 after, of course, we close RFD, and then CFD doesn't exist here, so we'll just close FD. Very good. So we'll do a little GCC. We'll do GCC tac O client on client.c. We'll get one warning as we didn't include standard lib for close. That's okay, though. We'll ignore that for right now. So we can do two things here. I'll make another tab. So we'll do the server up here and then the client down here. So we first of all should see an error by not specifying the IP address. Great, so we do get that error. And up here, the server won't actually do anything when we get the connection. So to show the connection coming in, I'm gonna do an strace. The strace command, what it does is it shows every system call the program makes. So you're seeing socket happening here, bind, listen, accept, etc. And the accept is blocking, meaning the program is no longer running and it's waiting for our connection. So if we now run our client and do 127.00.1 or the address in a string form of localhost, and we hit enter, you'll see that our client went out, it connected to the server, accept returned a new file descriptor, and then it closed it. And I can actually run this whole system over again, and we can do an strace on client, and you'll see the same thing happen, right? We create a socket, what we call connect. Connect returns 0 because it connects to the port, and then we close that socket and leave the program. So that's how we write a C server and socket. Say that 3 times fast. In the next lesson, what we're going to do is we're going to actually exchange some data between the two. We'll kind of show how we can use structures to begin to design a protocol and how we can send structures across the two sockets and maybe some do's and don'ts of sending data in C. So we'll see you in the next lesson. Take care, guys. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. In our previous lesson, what we did is we created some cool stuff. We made a server that can sit here and listen for a connection on the network on any IP address, and it listens on port 5555. And then we also made a client that we can strace and watch it connect to the server. And that's all it does right now, right? We can see with strace that the connection happens here. The syscall goes out and does the connection. We close the socket afterwards, and the connection is seen up here in the server. So we are going to add some functionality to this. I want to show in this lesson the basics of how sockets are treated from a data transfer perspective, where to the kernel, the socket is just a file, and like a file, you can just read and write data to it. Very cool. And also, like a file, you can write and read arbitrary structures out of memory in C, and use that to transmit your data. So what we're going to do is we're going to design kind of like a loose protocol. It's not like a real protocol. I wouldn't use this in production, but I want to kind of drive home the idea that all you have to do in C now, once you've gotten the server connection set up, is figure out a way to meaningfully construct data and send it to the server, and then like you're good. So we have our server here, and first of all, I want to add that our server does close after every connection. The way we can fix that is by adding an infinite loop here. I know it's bad practice, but just for the sake of example, we're going to take all this code, put it in this while loop, and note that we have the close and the int CFD declaration inside that while loop, and we'll also tab this in so that now when we every time we can create a connection, we accept a new client, we do something, and then we close it out, and we can actually see that this works up here by doing GCC running the server, and now we'll see that we can run the client multiple times. Every time we get new connections and the connections are not getting blocked, the server is not dying. So very cool. So what we can do with this now is we can make a function on the server side called, we'll do handle client. This will take the CFD or the client file descriptor, the socket, as input, and that's going to just be the function that we use to handle the connection, to do our data exchange, and basically run the protocol we're going to write. So in handle client, which will take an int fd as input, not ferd, an int fd as input, we can do a couple things. We can read data from that client. We can write data to that client. And this is on you as a protocol designer to figure out what are the things that we want to exchange. The example we're going to do is we're going to exchange between the server and the client the protocol version, right? You want to make sure that the server and the client, as maybe your program gets older and you want to talk about backwards compatibility, that your server and your client are talking the same version of the protocol that you design. How do you do that? Well, you communicate the protocol version and you maintain a versioning scheme for what features are and are not included in different versions of the protocol. So we're going to create two structures here. We're going to say type def struct, and we'll call this a proto header t. And the proto header t is going to be just the header of our protocol, right? So it's going to have the length of the protocol and also the type of the field that is contained in the protocol. So then also we need to create an enum. So we'll do type def enum, and we'll make the enum called proto type e, right? And all we're doing here is we're creating a field and a named field that will represent the different types of protocol headers we can have, right? The different types of packets we can have. So the first one we're going to have is a proto hello, right? Which just represents a named number that is going to represent the hello message in our protocol. And then we're going to say that we have a proto type e, which is a field. Sorry, I don't want to actually name this uppercase. I want to make this lowercase just from a naming perspective. Prototype e, this is the type of the field that we have. So we'll lowercase this, let's call it a proto type e, and then it's going to be called the type of the packet, and also we're going to have an unsigned int len. Actually, our packets are never going to be bigger than like a word size than an MTU. So we'll do unsigned short len, and then this is just the header, and within this will actually contain the value. And what we're actually constructing here is known as a type length value system. So if you've ever heard of this TLV, right? When you have information you want to convey between two places, typically you convey the type of the data, how big the data is, the length, and the value of the data afterwards. So what we can do now is we can create a buffer in our handle client function to represent where we're going to put all this data and set up our packet to send it over the wire. So first we need to actually create room for this data. We're just going to make some random number right now. We'll do 4096 bytes on the stack. This is, just kind of dead space for our memory to work with. And then we're going to make a new pointer called proto header t my header is equal to buff. So we're just going to set that equal to the buffer value so we can work with the buffer as a named structure, right? So then we'll say that the header type is equal to a proto hello. And then we'll say that the header len is going to be just 4 bytes, right? This is going to be the length of the data that we're going to convey, which will be one integer. So it's going to be 4 bytes long. And then at the end of all this, we're going to have to create a pointer to the data that's going to be put into the packet here. So we'll say that the we'll call it the int pointer data is equal to an int pointer of header of 1. Now, I know this may look a little confusing. What we're doing is we're constructing our header, right, in this one location. It's a single header. And then by treating this header pointer as an array, we're indexing one header past it and then converting that into an int pointer, right? And now we can say that the thing pointed to by data is actually going to be the value we're conveying, because we have type length and then value immediately following it. And then the value is going to be protocol version 1. Now we're almost done, but there is one more thing we do have to handle here. We need to be able to handle the endianness problem. And don't forget, all of these things are host endian by default, so we need to put them into network endian. So we'll say host to network long here on proto hello, and we'll do host to network short on 4. And then this is also going to be packed networks. We have to do host to network long. And again, none of this is production code. This code is just for an example. What you want to probably have is a function where you construct your packets separately, and then a function that you pack your packets separately, right? You do the network endianness on them. But once this is all constructed, we can write to our file descriptor, the client socket, and send it this data. So we're going to send it starting at the address of header, or the address of the header, which is just the header pointer. And then the problem and the thing we're going to send is the size of the header, which is just the header itself plus header len, right? What this means, we're going to send size of header, the header structure, plus the values contained in the TLV, which is the 4 bytes, which is the data integer, right? And probably this 4 should actually be size of int, because the integer size in theory could change, and this is all now making the compiler happy. But before we do all this, don't forget we have already packed our header len to be corrected for endianness, which means if we use it in any math in the future, then it's not going to be right. So we do have to do one additional thing to make sure that our packet actually gets sent the right amount. So instead of doing the endianness check here, we'll do header len is equal to the size of an int, which is the size of our value. And then we're going to have another variable called int real len is equal to header len, just to save it somewhere temporarily. And then after that, what we're going to do is we are going to then pack the things. So say header len is equal to host to network short of header len. Very good. And then also size of header. Header is a pointer. We don't want to do that. We want to say size of proto header t, which is more technically syntactically correct. So we'll take that. And now we are set up to actually, oh no, we also want to remove header len. We want to do plus the real len. Very good. So now we are able to transmit the size correctly of our protocol. And we can do a little bit of GCC. We'll strace that to make sure it's working correctly. And then we can go into Netcat and then see that we're not only getting the protocol type, which is 0, it's got 4 bytes defined as the short. And then we're also getting some padding, which we'll talk about later, but then the protocol version, which is awesome. So what we can do now is go ahead and take this code and put it into our client, and we're going to use the client to do a basic exchange of information between the two. We'll do kind of a handshake, right? So we take this code. Now, it is important to realize that because this code is going to be representing a protocol, we want the types to all be the same. We should put this into a separate C file. I'm not doing that right here in this tutorial, just for the sake of example, but you should be putting this into a different C file. We'll talk about that in the final project to make it so that the protocol files are all the same. So I'm going to copy all of this code out of server.c and put it into client.c because the code is mostly going to be the same. Very good. So these types are the same. So we have a buffer, and instead of writing to this buffer the same way we did, we're going to delete all of this. We're going to say that we will, because we expect a protocol type T, we are going to just read into the buffer from the FD the size of a proto header T plus the size of an int. And then once we have all these things, we are going to do the same thing we did before. We'll do that the proto header T pointer header is equal to buff. We'll say header type is equal to host or network to host long. We have to unpack it of header type. We have to say that header len is equal to network to host short. We're taking the version from the network, putting it into host endianness. Network or header len. And we also have to unpack the data. Same thing as before. So we'll say int pointer data is equal to the address of header of 1, right? Very good. And we'll say that the thing pointed to by data is equal to host or network to host len of the thing pointed to by data. Very good. And now once our packet is all unpacked and it's put into the proper endianness, we can do some checks. So we can say if header type is not equal to proto hello, then we can say printf protocol mismatch failing, something like that. And then also you can say if header or if data is not equal to 1, right? Our protocol version, printf protocol version mismatch failing. And in these failures, we can also do things like return -1 or just return, because we're not returning types right now. But this is where we have the chance to actually do an error system and return what type we kind of got and break these out into functions. But again, for right now, we're just doing kind of a proof of concept to talk about how this all works. So we have checking our types, checking the data, and then we're returning. And then if otherwise, we could do printf server connected protocol v1. Very simple stuff. And we'll do a new line here, close that out. Also do new lines here because we need new lines in our printf statements. Oh, sorry, not if data, is if thing pointed to by data, because this is a pointer and this is a value. So see, even people that have been doing this for a long time make mistakes. There we go. Server connected protocol v1. So there you go. At a very high level, we have created a basic protocol using structures, sending data between the server and the client. Now, in the next lesson, we're going to move on to a couple niche topics like socket options, things like that. After that, we'll move on to multiplexing. So in a world where we have multiple sockets that are open at the same time, how to do a state machine to pull and select off of those. And then after that, we're going to enter into the final project and take the ideas that are pretty simple here, like just creating sockets and connecting them together, but using that to design protocols so we can do the employee database across the network. So we'll see you guys in those next lessons. We'll take care. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. So in this lesson, in the next couple of lessons, we're going to be talking about this thing called multiplexing. So multiplexing is this idea in programming where you're trying to handle different data from different sources using synchronous I/O. The problem kind of arises in programming when you do what we did in our previous lesson, right? We have this server code and we do the traditional bind, listen, accept, but all of the calls that happen in this code are what is called blocking, which means the code will literally halt execution. The kernel will block the program until the I/O returns, right? So for example, in this accept line, we will only run the next line of code when accept returns, obviously. Now, two things have to happen for accept to return. A client has to connect, or the socket that we're using has to close or have some kind of error, right? And we handle that all here. The issue is if we then have two clients that want to do some operation with our program at the same time, we literally can't do that. And for example, let's say we accept a client. The code is now running in the handle client code, which handles the data I/O of the client, the read, the write, whatever. But then a second client tries to connect. Because we're not in a blocked state where we're blocking on accept, we literally are unable to process this connection, right? Until we get back to the place in this while loop while we're accepting. And it may seem like in your head, maybe you have a simple solution for this using the accept calls and the read and write calls. But as you scale your program to have multiple states, like you want to have it reading and writing different kinds of information in like a state machine where there's like a connected state, a ready state, and a closed state, while you're also trying to connect other connections, it's going to get extremely complicated, extremely fast. And doing it using these blocking I/O functions is really not possible. So the way that the Linux kernel has this solved is by using a function call called select. So the way that select works is really interesting. So instead of passing it in a single file descriptor and letting it block against that operation, what happens is you pass it in a list, or what is actually referred to as a file descriptor set, of file descriptors that you want to check to see if they're readable or writable. And then what happens is when an operation happens on any of the file descriptors in the kernel that makes them available to be read or available to be written to, select will then return. Then what you can do is you can iterate over all of the known file descriptors and check to see, hey, of the file descriptor set that I put in, is that file descriptor set? And if it is, that means, for example, that the file descriptor is readable and we can read data out of it. What this allows us to do is read from n number of clients, where n is the FD set size, which is a variable in the Linux kernel headers that says the maximum size that a file descriptor set can be. On my system, it's 1024. On IBM systems, it's 65535 UMax short. So, you need to be aware that FD set size is not set the same across all computers, but this allows you to do synchronous multiplexing, which adds a lot of power to your programming repertoire, right? So what we'll do today is I'm going to walk through some code that I wrote. It takes a lot of code to make this work effectively, so I don't want to type code in front of you. We're going to walk through some code that I wrote, and I want to kind of explain what's happening, and I want you to take the same idea and try to write a piece of code that uses synchronous I/O multiplexing using set. The next lesson is going to use a function called poll. I'm not sure if I saw it in this page here. No, it's not here yet. But select is an older version of synchronous I/O multiplexing. There is some argument in the Linux community that select should be deprecated and poll should be used, kind of a newer function with more functionality, more features. But I think it's important to know how select works because select is still used in a lot of legacy code bases. So with that being said, let's dive into the inner workings of select and how we kind of design a state machine or a server around select as opposed to just like raw blocking I/O. So we have the select example here. And what we're going to do in this code is effectively create a global structure that represents a single client, right? So we have client state T, and the client state T tracks a few things. One, we have to obviously know when a client is connected to us, what is the file descriptor associated with that client. And what's cool is that we can actually create an array of these clients and then use their file descriptor as an index into that array, right? And I'll show you how that works with the select down at the bottom. But effectively what we're going to do is create an array of n possible clients where the clients is the FD set. Right now we're just doing 256, but this should in theory be 1024, right? But we'll do 256 for right now. And within the client state, we're going to track not only their file descriptor, but also an enum that says, is the client new, connected, or disconnected, right? And what that allows us to do is see if the state is available to be used by another client. And then also we want to give each client their own buffer. The reason for this is I like to segregate the data that clients use. Like in theory, in our main event loop, we could make a single global buffer that's global, right? But it's like global to all the clients. But giving them their own space in the BSS allows us to give them their own kind of privacy. And in theory, if we're not sharing logic across these buffers, it should add a little security to the program. So we create this client state T, a global client state, and then we have some like basic functions that initialize the clients, right? So because these are a globally defined structure, we have to assign their value, right, at runtime at the beginning of the program. So what we'll do is we'll say that the FD is -1, which is an invalid FD. And so -1 for us will indicate that this is a free slot available to be used. And obviously when we set the FD, we'll use that to indicate that it's currently in use. We'll also say that the state of the client is currently a new state, and then also we'll mem set out the buffer. We'll say that it's all 0 to make sure that the buffer is clear and there's no data in there from the previous user. And then we have some basic functionality where we have find free slot, where we're going to iterate over the entire list of clients. And if the FD is our known free value, we'll return I, where I is the index of that free slot. And if we can't find anything, okay, well then the server is wholly occupied, meaning that the clients we have 1024 clients connected, and we can't add any more clients. Okay. So here what we're going to do is we're going to create some basic structures, and I'm just kind of hitting these out to kind of make them a little easier for you guys to read. The listen FD is just the same as the previous server, right? So we have the FD for our socket that is going to receive the connection. So don't forget, in any socket application, you have the listening socket that's listening for connections. And then when you accept, you create a new file descriptor to represent the connection between you and the client, right? So me and the client talk on one FD, I accept clients from another FD. So this is going to be our listening for clients FD. This is the connection FD. So when we accept, we're going to temporarily save that FD in the con FD variable, and then we're going to write it out to the FDs that are in that global list. We have our NFDs, which just tracks the number of file descriptors we're currently tracking. This is going to go into the select call in the future. Then we have our free slot, which is a variable we use to track what is the next available slot we can put somebody into. This doesn't change. This is just the server address and the client address, and we have to set the client len, obviously, to accept what type of client we're accepting. And then this is kind of the new functionality, right? So we have the structure called an FD set, or a file descriptor set. And literally all it is a special structure in libc that allows us to indicate when we call select, when it returns, what file descriptors are readable and what file descriptors are writable, right? So we have these here. We use that to track which ones are available for action. And then we have init clients, right? So that goes through, that iterates over the entire list, and that clears it out, makes it available for us to use. So this is where, basic, socket IO stuff happens. We have to still create our socket. It's an AF INET IPv4 TCP socket, pretty straightforward. And then just like before, right, we clear out the server address to be nothing, and then we set up the variables. So we listen for an IPv4 connection on any named address on us, 0000, and also on port, whatever port is. Port, I think, is 8080 in this scenario. And then just like before, we do all the basic stuff. We do bind to turn the socket into a passive socket to listen, and then we call listen, right, where we can listen for some backlog. We just choose 10 here for whatever reason. And obviously, like any good C programmer, we are checking for the return value, and if the return value returns bad, we say what the error was, and we exit with an exit failure, which is -1. And then once we've gotten through all this, we tell the user, yeah, we're listening on port N, where N is the variable here. Now this while loop is our main loop in the function, right? This is going to contain all of the logic to do synchronous IO multiplexing using select. So whenever we use an FD set, when we want to eventually use it later in the program, we need to clear it out. Like you can think of an FD set as like a bit mask, right? It starts out as all zeros, but then when we do select, it'll set a bunch of ones, right? You can think of it kind of like this, right? And we can use some logic to iterate over it and see which of the FDs have been set. So what we have to do before we actually go through and use it is put it back to its known good state, which is all zeros. So we do that by calling fd0 on the FD set. So we clear out our read, clear out our write, and then we want to check to see if the read file descriptor is available. Now, we want to check to see if the listen file descriptor is available, so we have to set that in our FD set. So what we're doing right now is we are adding bits that we want to check to our file descriptor, right? So we're adding bits we want to check to our set. So we say, first of all, I want to check to see if the listen file descriptor is readable. And what that means, if it is readable, is that a client is waiting to connect. So we have to check that to see if a client is connectable. And then the way that select works, when you do eventually call select, you need to specify the number of FDs, right? The highest possible number that is available. So what you're going to do here is say that the number of FDs is equal to listen FD plus 1. You have to add 1 to it. It's like the maximum value. And then what we're going to do is we are going to also add active connections to the read set. So what we're going to do is we're going to iterate over all of the possible clients in our global client list, right? If that global client list isn't, or if that single client is not -1, we're also going to add that to the read set. So what that means is we're going to say, not only are we checking to see if an active client connection is available, we are also going to check and see if a known connected client, meaning that it doesn't have a -1 FD, is also available for a read, right? And then also, if that FD is currently greater than the highest FD, right, the NFD's variable for select, we're just going to say that NFD is equal to client states FD plus 1. So we're just keeping that maximum value higher and higher. It has to be the highest value that it can be, plus 1. And this is where the magic of select comes in, right? So here we're setting FD to tell the select function call that we want to check for that FD's IO state. Is it readable? And then once we set all that stuff, we then call select. The arguments to select are, like I said before, first of all, the maximum value that can be selected. Then the two sets that we're checking for, the read FD and the write FD, and then the other two are not really important for us, but there is a except FDs if there's exceptions on those file descriptors, and then also a timeout val. By saying null in the timeout val, what will actually happen is it'll block until one of these FDs come back. So we're going to block on select. Now, again, don't forget, you're probably thinking that we're still blocking, so what do we actually solve here? But the problem is, or I guess the main difference is, we're blocking on all possible FDs. So once we get done blocking, if 2 FDs came back positive, we can just go take care of their connections, right? So when select eventually returns, we are going to have inside of the set the remaining bits that are available to read. So like I said, for example, before, first when we did FD0, we had all of these zeros set. Then we said, hey, I want to check this guy and this guy and this guy, right? Then we call select. And then after select runs, let's say, for example, that this guy is set. Interesting. Okay, so we have to now go take care of the logic that says that, we read off of this guy, because this means that there's still blocking data. It's waiting to be read from. Now, this is the main issue with select, right? There's no way to iterate over a file descriptor set. What you actually have to do is just know what the max value is and then iterate over every single file descriptor and then check, is that FD set? Now, there is one edge case we're going to handle first. Is the FD set of the listen FDs, right? So let's say, for example, the listen FD is this guy. If this guy is still set after select is called, that means that we are waiting for a connection, or a connection is waiting to be accepted from our program. So we have to handle that logic here. So if we get a new connection, we're going to run accept just like we did in the previous server, right? This is nothing new. We just, bind listen, and now we're accepting because this FD has readable data. We accept into the client address, and then if we fail, we block out of it. Otherwise, we tell the user, hey, we got a new connection, and we say where they came from. It's the SYN header and the SYN port. Very cool. And then we have the FD saved in confd. We need to find a place in our global structure up top to put them, right? Because there's a list of all these clients. We got to put them in a spot. We don't know which spot to put them because we have to find a free available slot. And that's what find free slot does, right? So find free slot will iterate over all those functions or all those variables and find a free slot. If the free slot comes back as -1, hey, all the slots are indicated as full. Sorry, can't help you. Close out the FD. Otherwise, all we have to do is say that we put the FD of that variable or of that client into this slot, and we change the state. Now the state is connected. In this example, I'm not going to use the states too much, but what you're able to do when you have a state associated with an FD is you can per readable event in select, you can do an entire finite state machine to handle what kind of data, right? Because what if you have two clients, A and B, where one hasn't even received the hello packet yet, but the other one is in the middle of some kind of like data IO to like send an employee, for example. You want to track using a finite state machine what state you're in. We'll handle finite state machines in the actual project design for the next lesson. So with that being said, we have the state connected and we're good to go. So we've now handled the edge case of like, okay, is the listener FD set? If so, cool. Now what we have to do is handle every other client in the server, right? And what is the maximum thing we're going to iterate to? It's the number of clients. So first of all, we're going to iterate over every client in the client list and say, is their FD even set? Because if the FD isn't set, like I don't care. Like we don't really have to worry about this. But if the FD is set to a valid file descriptor, we then want to check, is that file descriptor still set in the bitmask? Because if it is, like I said before, we have all of these guys were not available, but oh, that guy popped up. That means that he is still readable or she is still readable, whatever. So we can take this file descriptor that is now set based off of is set and then read from it, right? So then we call FD, we call read on that FD, we read into that client's buffer, and then we get n number of bytes back. N number of bytes, as seen before from read, if n is less than or equal to 0, we know that they are now in a closed state, right? Read would not return with 0 or less than 0 unless you close the connection or it's in a bug state, right? So bytes read comes back as 0. That means we have to handle the close out the client state, right? So we'll close the FD. So that closes the connection at the TCP level, but now we as the server are responsible for cleaning up their memory, right? So there's FD here, set it to -1. And then also state, we have to set it to disconnected. There is a security vulnerability here. And I'm curious, for those of you that are now learning C for the first time, if you can kind of detect what the bug is. So consider from a privacy standpoint, what if two users get the same slot, right? If one connects, disconnects, and another guy gets that slot, what could we possibly do that's kind of evil in this program? Anyway, if the bytes we get back are greater than 0, great, we have data. We received the data from the client. So that's the code at a really high level. That's exactly what it does. That's how we use select to do non-blocking, or I guess blocking, but blocking once, synchronous IO. Okay, so we're going to walk through actually running this program, and I want to kind of show you how it looks in the S trace, right? Because what we'll do is we'll do foreground. So we run this, and again, I want to really emphasize when you're learning to code in C, and especially when you're doing lower level, like using the POSIX API coding in C, it's really, really important that you know about the strace tool, because what it does is it traces the system calls, right? So you can see exactly what not only the functions you're calling are, what their inputs are, but the return value and potential ways your program breaks. Also, it teaches you kind of how the functions behave because it gives you an idea of when they return and stuff. So what did we just do? We are currently blocking, and the way we know that it's blocking is that the function is not returning. We don't get a return value, right? We're currently in select. Select is currently being called on 4, where 4 is that NFD's value. So 4 is our listening socket, because we can see the socket gets called here. That's our listen socket. It returns 3, so we call NFDs being 4, so it's the max plus 1. And then this is our read FDs, and these are our write FDs. So we are currently asking select, hey, I'm going to give you the number 3, which is the listening socket. I want you to return when one of the numbers in that set, which is only 3 is available, is readable. Okay, so what we can do is we can now connect to our server by using Netcat localhost 8080, boom. Okay, so we're now in a connected state. And you can see that when we did that, select returned, and that there was one file descriptor that was available in 3. It has to be 3, obviously, but our logic ran. And then when we checked to see if the listen file descriptor was available, we saw, oh, it is. We called accept, and then we got a new client. Now what's happening is we added that new client, the number 4, it's behind my head, you can't see it, 4 to the file descriptor. Very cool. So we added that file descriptor to the file descriptor set and then called select on 5, which is 4 plus 1, the max file descriptor. And now we can do 2 things at the same time. I can both send it data, and in another window, I can connect to it, and we can see that we're getting both. So we not only called select, it returned that 1 is available. I read the data, but then we also, after that got done blocking, we got another connection, and now we can do IO with both of these. I can send one here, I can send one here, and you can see that we're getting data on both of these sockets. So that is the power of synchronous multiplexing, so synchronous IO using select. I hope this makes sense to you. Please, please, please do not move on to the next lesson until you've written just basic functionality. It doesn't have to be as complicated as this. It doesn't have to have like state machine or whatever, but write a function that uses select and use it to have 2 clients connect to you at the same time. It's a really, really interesting way to think about IO when you know functions block, a way of making your program block, but in a way that's effective for multiple connections. Also, I'm going to have another course in the future called Threads That Don't Suck, or I forget what I'm calling it, but it's effectively a way to do this using asynchronous function calls, like using threads. It's important to understand that it's really easy to make a program that has multiple connections a security vulnerability, because there's no like formal way of blocking access to these things other than the logic of your program, right? So if you have like a logic error or something, like client A and client B are accessing memory that's in the same memory space, right? So in theory, like you could break this and do evil things. But anyway, that's for a future lesson, a future course. I hope you enjoyed this. If you did, thanks, great. And we'll see you in the next lesson where we talk about poll, which will be a little, I think, easier to use for maybe people that are new to the programming language. Okay, goodbye. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. So in this lesson, we're going to kind of update the code we had before that was using select to use the new function poll. And again, the whole point here is that we're doing synchronous multiplexing for IO for a socket server that wants to have either multiple connections or have, connections while it's listening for new connections, stuff like that. So again, consider the case that we have client A, B, and client C. Client A and B are both connected to the server, but maybe they're in like different send states, right? Like one is still in the state machine where they're doing like a hello packet, and the other one is in the middle of a data send, right? And then client C hasn't even connected yet. We still are like waiting for the connection. When we're using blocking IO, like accept, read, and write, it's very hard to do all of those things synchronously without making one wait for the other. If we can use a function like select or poll, we're able to reduce all of the blocking to one function and then handle all of the logic after that single block ends. We talked about this before, but it's a bit of an argument in the community for Linux if select should be deprecated or not. The reason why select gets a lot of hate is that, like we kind of showed before, when you're doing the call for select, instead of having like a list of FDs you want to check, you have this thing called an FD set, where the FD set is as wide as the maximum number of FDs you can set. And then it kind of treats it like a bit mask. So we put in that we could potentially have 1024, and it says, okay, so this one's good, and this one's good, waiting for read, and this one's waiting for read as well. And then what we have to do is literally iterate over every single FD in the set and check, is this one set? Is this one set? And computationally, this gets a little expensive, and it's not the most straightforward way of thinking if you think of just basic imperative programming, right? The way that poll does it, poll is a little more straightforward, where instead of giving it just some number and you say like, here are n number of function or file descriptors that are available, you literally specify just a list of FD structures, the events you want to check for, and then how many events are in that FD structure. So we're going to walk through our code here that I updated to make compatible with poll, and you'll see that it's a lot more logical than the select example. The code doesn't change much. in the beginning. We have here the init clients. All we're doing here is we have our global client state structure and then the array of those structures. And we're just setting the default case to be that the FD is -1. That means that the slot is free. We can store info in there. And also the state is a state new object. Again, we're not using the finite state machine too much in this example, but it's just good to know that you could do a lot of statefulness tracking in a structure like this. And then we want to set that global buffer to be 0 because we don't want to expose any private info to the user that connects to us. The function find free slot is the same, right? We have to find a free slot in that global array of available client slots and then return the index of that slot. And if there are no free slots, we return -1 and handle it appropriately. We do have a new function introduced here, find slot by FD. So before, what we were able to do is index into the client states array based off of the FD. The FD could specifically just be an index into that array, right? Because we are doing a structure where there can be less FDs being checked than there are slots in use, right? Like let's say, for example, I have 4 clients connect and then 2 of them disappear, right? So now I have FDs 3 and 6 open. Because those are not adjacent, I now need to have a function that returns a slot ID as a function of the file descriptor. And if you're confused by that, we'll talk about that when we get to it. So yeah, and again, we return the FD as I, and if it's not found, we return -1. We handle it appropriately. In our main function, none of the objects really change here, none of the classes change, or none of the structures change here. You know, you have the file descriptor for the listener, the temporary connection file descriptor for when we accept a new client, and then our integer to track a free slot that we're going to use to put the new client into. You have your sock adder in for the server adder and the client info when a client connects, and then you have the length of that client info just to track that it's the proper type. So here we're introducing our new PollFD structure. So this is where poll gets a lot of power. The way that PollFD is structured is there are 3 fields. You have the PollFD, you have the FD field, you have the event field, and the REvent field. I'll describe this in the code later, but the way it works is the .fd for one of these is the file descriptor you want to check for an event. The .event field is which event you want to check for. And then there's another field called .rEvent or received events, which is the event that actually happens. So if you put in an input event to the event field, you call poll. If the input event or a readable event is available, the REvents field will specify that. And we'll show you how that works in the actual code. Here we have the NFD field, which is going to just track the number of current FDs that we're tracking. So again, the NFD field in our previous example for select was the maximum amount of FDs that were available, the highest number, which is not very smart, right? Because that means if we have FD3 and FD12, it's going to check 3, 4, 5, 6, 7, 8, all the way up through 12. What we can do is just track the number of FDs that we're currently tracking and not have to worry about anything in between those two, right? Again, the primary issue here is that FDs are not sequential. Like they don't have to be. Like there could be an out of order connection where it's like sockets 3, 4, 5 get connected, but then 4 drops out. So you have only 3 and 5. Select would require you to check 3, 4, and 5. Poll lets you check just 3 and 5. So same thing as before. We initialize the clients. We do our listen, our SetSockOpt to make the socket non-waiting. And then we memset the server address, and then we bind, listen, all that good stuff. This is where the first use of our new poll structures come in. So just like in our select example, we want to check the listen FD for a readable event or an input event. What this does is this gives us the ability to check to see if the listen FD has an incoming connection we need to accept. And if that happens, we need to handle that separately from the rest of the sockets. So we say that the FD is the listening FD that will accept the connection from, and that the event is an input event or a poll in event. And then currently we have one FD to track. Now this is the main event loop we're going to use to handle all of the input. There's 2 main cases, obviously the listen case for the accepting socket and then the rest of the clients. Now the major difference between select and poll is the way we set up the structure for calling the system call. So previously, right, we created an FD set, and then the width of the FD set was the largest file descriptor plus 1. What we're going to do here is just iterate over all the clients in the global client structure. And if they still have an FD, meaning they're actively in use, we're just going to add that FD to the FD, the PollFD structure, right? And say that it's an input event and then increment this inner counter. So it's effectively mapping client states of, the client state buffer, the client state structure to the PollFD structure. Very simple here. So if we have, slot 1 and slot 255 in use, FDs are only going to get 1 and 255. It's not going to have to do all of them, which is really powerful. Now, we eventually do call poll, and the way that poll works is, again, we specify that FD is structure. That's our array of PollFD structures, and then the number of FDs that we're tracking, right? So this actually gets set in the accept function, which just tells us how many clients we're currently tracking. By default, it's 1, but when we get new connections, we add 1 to it. And what's cool is that poll returns the number of events that are waiting. And we can use this number of events that are waiting later in our function to handle the logic for decrementing that when we handle an event, right? So if we have n events equals 3 and we accept 1, now n events is 2, we now know that we only have to handle 2 readable events. It helps us computationally reduce the amount of FDs we're checking. So first, we need to check the edge case of, is that first FD, our listen FD, waiting for input? If the answer is yes, then we have to handle that by accepting it using the standard, accept client addr client len. And then we have to put that new FD, the connection FD, into a slot. So we'll do like we did before. We'll find a free slot. If we don't have a slot available, we'll say, sorry, so sad, we don't have a slot, and we'll close it. Otherwise, we take the free slot of our global client state structure array and put that inside of it and change the finite state machine. And again, we're not going to use FSM too much, but it's an idea that you could track an FSM and use that to handle what event takes place based on the current state. And then, like I said before, the NFDs now goes up by 1. So this tells the server we are tracking 1 more FD that we have to handle event tracking for. And then we're just going to print that slot N got FDY, right? Or slot X got FDZ. Slot X got FDY. And this also helps us track the number of events we have to process, because now that we've handled this accept, we now know that the number of events to handle for this loop goes down by 1. And then right here is where the rest of the meat and potatoes are. So let's kind of walk through what's happening here. So first of all, we've already processed 1 event, right? I less than NFDs, meaning we have to go through all of the FDs that we're tracking. Do we handle the rest of them, right? So this is assuming that we're going to ignore the listen FD, go handle the rest of the FDs, right? We're checking every single FD that we could be tracking for an event. And also, if we're out of events to track, then don't do this, right? If we don't have any more events left to handle, then none of this matters. There's no more data. So in the event that we have more events to handle, we're going to check and see, is the FD structure, the received events, a poll in, meaning is there data to read off that FD? And if the answer is yes, if this bit mask is true, we'll reduce the number of events to handle by 1, so we don't have to do any additional processing if we don't need to. And we're going to pull out the FD from that event, right? And again, we don't have a system set up where the clients are contiguous in that global structure. It could be client slot 1 and client slot 255. So we have to look up the slot by FD. So we say that FD 7 yields client slot 6 or something, right? So we're just getting that slot. So if we need to handle any information, we can handle it in the next part of the function. So given that FD has readable data based off of the result of poll, we'll read from it, right? And we're going to read into where? The buffer of the client associated with that FD. And again, that slot came from here. We'll read into it the number of bytes that are possible to come off the network. And if we get less than 0 or equal to 0, that means that there is either an error or a closed function. It means there's either an error or a closed socket. So we'll close it out, and we'll get that slot again from this function. If for some reason the slot returns a -1, this is an edge case. This shouldn't happen, but we should be checking for it. Otherwise, we'll put that client slot into a closed state. So we'll say that the FD is now -1, the state is disconnected, and we'll also decrement the number of files descriptors that we're tracking. And then finally, all we have to do, the only thing left to do, is if we received data and there wasn't a closed state, we're literally just going to print out that data, right? We're going to say, okay, cool. So he gave us this data, they gave us this data, client slates of slot.buffer. Very good. And that's it. That's all we have to do. So by writing the code this way, we're actually able to really easily handle one special socket for accepting new connections, and then writing this loop to read in data from a socket only if it's blocking and has waiting data, right? Really, really cool stuff. So let's go through and trace this and kind of show you how it works. So by running strace, we start in the state, we do the traditional socket, AF, INET, blah, 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 blah. We get 3. And then we do SetSockOpt to make it non-blocking. That actually is in a future lesson. You'll see in the next lesson. But then we do poll. And what does poll take in? Poll takes in that array of file descriptor poll events. That array of PollFD structures, where the FD is currently only our listening socket, FD3, and also it has a poll in event, meaning we're asking the kernel, hey, is this a readable event? Is there data waiting on that FD? And it's not going to return anything until any of these are true. Right now, none of them are true. And 1 is the number of FDs, and then -1 is the timeout, which there is no timeouts. It will block until it returns. So we can go into this window here, and we can do netcat to the server, hit enter. And because we got an event, it returned 1, which is the number of events. It returned that FD3, which is our listening file descriptor, has a poll in event. That in our code triggers the logic here that because FD0 has a poll in, we can call accept, which yields a new file descriptor, which is our connected file descriptor. We're putting FD4, our new FD, into slot 0, and now we append that PollFD structure to the array, and now we're also checking for input on that socket on PollFD. And now we can do 2 things. We can, while we're also sending data via poll or via this connection, we can in a separate window connect the new host. So now you'll see we at the bottom here in the poll are able to listen to 3 separate sockets. The first one being our magic edge case for handling new connections, and then 2 different clients. And even then we can hit Control-C to disconnect, and the server will detect that. It'll say we got a read on FD4. It was 0 bytes. We had a disconnection, and now it is no longer in the PollFD list. And I can do it again on this one. And now we're just back to the regular state. So this is poll at a really, really high level. There are probably ways to write this code better. I really, really recommend that you take a step back from the course for right now. You think about this. You go for a walk, and then you come back. And I need you guys, before we move on to the class project, to write a basic function with poll, right? Write a basic piece of code that using the PollFDs can read from 2 different sockets at like the same time, right? Not the same time, but like using synchronous IO. Because the rest of the course project is going to be very dependent on understanding how this works so that you can take this and use it to implement a finite state machine for each client. So with that being said, I really hope you enjoyed this. This is where C starts to get crazy. You start to use the synchronous functions for multiplexing in the GNU POSIX API, and you can do some really, really powerful stuff. So take a break, take a breather, go for a walk, come back, go on to the next lesson, which is a little lighter weight, more about socket options. And then we will, after that, start the class project. See you guys there. Hey guys, what's up? Welcome back to your next lesson in network code that doesn't suck. So I know the last 2 lessons were pretty intense, a lot of code, very long lessons, new ideas, just a bunch of stuff being thrown at you. So I want to assure you that this lesson is a lot more calm, and hopefully what you learned in this lesson will teach you a new feature in the POSIX C API that will help you make your coding a little easier to run and debug. So in your adventures in coding network programming, you may have gotten an address that says like this address is already in use, where you run a program, you crash it, and then you try to run it again, and that socket is already bound, right? What we're going to do with the SetSockOpt function is override the default behavior of a socket. So what's happening in that example, for example, when you run code and then it binds the socket and your program crashes, the default behavior of a C socket is to be in a time wait state after the program crashes, and once that time wait expires, then the socket gets freed, and then you can reuse that address. The problem is, if your program crashes and you keep that socket open, you have no control over it. You literally have to sit there and like kind of just wait for your program to free the socket, right? So what we can do with things like the SetSockOpt function is override the default behavior of a given socket, right? And there are different options we can set for the sockets. So the one we're talking about today in particular is the reuse address behavior. So what this will allow us to do is have multiple sockets that are bound to the same local address and port. There are other cool features, like you can set it up to do a keep alive packet. So if the underlying protocol supports it, like TCP, for example, The keep alive option alerts the kernel that you want it to do a TCP keep alive every n number of seconds, right? You can do other stuff, like you can change the internal kernel send and receive buffer size. You can do don't route. There's a bunch of cool stuff you can do with these socket options, but I think the most obvious example and the easiest to display and to demonstrate is the socket reuse address function. So again, I don't want to bore you by typing out code for the rest of these lessons. So I'm just going to have pre-written code and kind of explain what's going on in the code, right? So this is very basic C code functionality for the socket server. Like nothing really new is happening here. The only new thing we're introducing is this SetSockOpt function. So there are two functions in the SockOpt family. There's get and set, right? So get obviously allows you to retrieve an options value and write it to optval. And then the second one is SetSockOpt, right? So if you wanted to check, for example, did I already set the socket reuse address option in this socket, you can use get, or if you want to set it, you can set it. So the variables that you give to the SockOpt value are obviously the socket that you want to modify, and then the type of thing that it is. This is a socket options socket level modifier, and then the option we want to modify, right? So we want to set on this socket, and the socket is SFD, the socket reuse adder option, which again is just letting us change the behavior of a socket so that bind allows us to reuse addresses. So if our program crashes or we want to do some tests, we're not like waiting for the time wait to expire, right? And then the opt value is just the value we want to set it to. So we want to enable the reuse adder option. So we're setting it to the address of our value, which is option. And then we also have to set the length of our option, and that's just the option value. And what'll happen here is we'll run SetSockOpt, and if it fails, we'll go to P error and we'll leave. Otherwise, it'll set the option to be correct. So we can go ahead and run this real quick, and we'll do an strace to kind of show you what's going on here. So we'll do strace on setsock. All that's happening here is the same usual stuff. Socket gets ran. We do SetSockOpt on 3, and the option is 1 here, and it's 4 bytes long. And then that came back with a 0, so good result. And then our program keeps running. Now I'm in strace and I'm blocking, so this does put our socket into a time wait state. But if I leave the program now, because reuse adder is enabled, I can run the same program and I'm not going to get a address already in use error. So go ahead, go play with SetSockOpt, see if you can add it to your previous pieces of code to make it work a little faster. Maybe you could, if you had that error before, you can bypass that error now with SetSockOpt. I wanted to do this at the end of the poll and the select lessons because I wanted to give you guys a break. I didn't want like the end of the module to be this huge fucking like dumpster of code. So that's it for now. Thanks for watching, guys. Appreciate it. I think next we're working on the class project. So get your ready your butts. Okay, goodbye. All right, guys, and so it begins. Welcome back to Network Code That Doesn't Suck. This module is our class lesson, our course project. What we're doing is we're taking the previous course project from Zero to Hero C Programming, our basic employee database, where we're able to run a program, open a file, parse some data, and add or remove elements to that file. We're going to turn that into a network appliance. Now, because of the amount of code we're dealing with, and I don't want to sit here and spend a bunch of time like typing out code and like correcting errors. So I'm going to make incremental changes to the project and then show you what I'm doing and explain to you the logic of the program. Also, so you can follow along with me, I will have this project broken out into a private GitLab repo or GitHub repo. I'll have the information on how to get access to it in the description for this lesson. The idea is I'll put it on GitHub. I'll have an encrypted zip file. You can download that and decrypt it with the password that's in the description. Again, I really, really, really implore you, please do not just read the code and be like, I understand. Like take the code that you wrote, that I'm assuming you wrote from the course project before, and add to it and make this happen. So in today's lesson, we're going to talk about kind of just where we're starting and the structure of this project, right? So the main idea here is we are adding some basic functionality to make it a socket server and to enable a client with a new program we're going to start to connect to it and query to list all of the employees in the database, to add an employee and to remove an employee, and then you can add whatever features you want and add that to the protocol. If you look at the main get option loop, we've made it so that all you can do is specify our database object file. If we want to make a new one or use an existing one, this should be deleted actually. And we also are able to specify with our get option loop a port number, right? So if we give it a P, it takes the port arg as a string, tries to convert it. If it's not correct, it fails and breaks out. And then we go from there. So we open the file, just like in the previous example, we print the usage of if the file path is not passed. We try to create the database file if we specify a new file in the flags. Otherwise, we open the database and we parse it out, validate the header. Like this is all the exact same functionality from the first course project. All we're doing now is we're calling into a new module that I'm adding to the program, right? So we talked about this in Zero to Hero C programming, but the idea is you want to treat every .c file as like a different unit of your code with its own special properties, right? The primary idea being not only does it make your code easier to read, it allows you to do better like group management if you're having multiple people edit the code. And also from a unit testing perspective, if you can get all of the single functionality of a particular module to live in one C file, it makes fuzzing and unit testing much simpler. So what we did is we moved all of the server functionality, like the three kind of like stateful things into this file here, right? So we have the definition of our client structure from the previous lesson with the poll state, the poll lesson in this file, and also the state of the server here. We're going to use this finite state machine system to handle the logic for when a client connects, right? So the way it'll work is a client will connect, we'll use a state that they currently are to determine what function to run, and that function will set the state of that client, right? So we'll have a basic finite state machine, and then all the logic for those state machine changes will live in server poll here. And then also we added, basically I copy and pasted the code from the poll lesson into here. We're literally going to use the polling loop that we built in the previous lesson, but now it takes a port number, the database header, and the employee pointer as an input, and then we'll use that to pass off to the functions that are dispatched when the event loop runs, right? So eventually we'll get here and we'll say we received data from the client. We're gonna add logic in this area to say like, oh, we received this packet and the client is this state. Let's go and do this thing. So that's kind of the system we built here. And then the make file also has been changed a little bit. Nothing too crazy. All we're doing is breaking it out into two targets. So the first target is target server. That's going to be bin db server. All we're doing is make it so that there are two subfolders, right? So there's source serve and source CLI. And in the compilation step, there's object serve and object CLI. When you type make, it tries to build both of these targets. Right now I've added the TACP option for our tests. When we build it, it'll run the poll server and hang, and we can run tests on the back end of that parallel using make. And then, yeah, so basically where we're at this point in the lesson is when I type make, it rebuilds the whole thing. And all that's happening is it's running the code from the previous poll lesson, right? It's listening on port 8080. And I can literally show you that like it's using the exact same logic. I can type this and it'll receive the data here. So what we can do now is we can receive the data from the client and use that to do kind of a handoff and begin our protocol for listing files, for listing the employees, adding employees, stuff like that. So in the next lesson, I'm going to talk about how to expand this to enable the finite state machine to accept data and use that to send an employee from the database to the client. So let's go take care of that in the next lesson. We'll see you there. Hey guys, what is up? Welcome back to the next lesson in network code that doesn't suck. Again, we are doing the course project. Highly recommend. Follow along, take some notes, write some code. Don't just read the code and say you get it. Please take the time out of your day and write some damn code. That's what you paid for. So with that being said, again, in the previous lesson, we kind of went over the new build system and the idea behind what's going to go on here. I'm going to walk through how I'm designing the protocol and how I'm designing the system for this project, right? So the general idea is that we're using the exact same code to open up and instantiate the list of employees that are available. And then we're calling this poll loop. And the poll loop is literally the code we stole from our poll example, only now at the very end, we're going to call this new function called handle client finite state machine. The idea behind this is we only run this one time for every time we get data from the user, right? So the function will take the database header, the employees, and the client buffer, like the global client piece that had their file descriptor and their buffer. as input, a pointer to that. And we're going to use all this information to run some type of functionality on that client, right? And again, the idea behind a finite state machine, we're going to write that function here in serve poll, is a finite state machine. Basically, you track the current state of the machine. So it's in like the hello state or the message state. And then based on the input you give the state machine, you change the state that you're in, right? So if, for example, we're in this hello state and we get the correct input, we can then upgrade to the message state. Otherwise, if we get the incorrect input, we're going to downgrade, I guess, to the error state. So the idea here is in the servePoll.h functionality, I've defined what the server will refer to as, a bunch of new states for the server. When a client connects, they're going to be in the connected state right up until they get to the handle FSM function. We're going to set the default state of any client that gets to that function when the client starts up to state hello, right? So it'll be in the hello state when a client connects for the first time. The idea behind the hello state is that to get out of the hello state, you have to exchange a set of messages. And I've defined here the basic kinds of messages that our new protocol or network protocol will support. So this is just an enum, which is, a numbered or a named number in C. And you have these types of messages and a request and a response, right? So here, I've defined a database proto header, and the header is going to have the type of message that you're talking and then the length of that message. And the length will not actually be bytes, it'll be the number of sub elements, right? So if you have the header is len2, that means that the packet below it will have 2 additional elements. And then below the header is going to be the actual elements we're talking about. So for example, in the hello case, it'll be the proto version. And then when we respond, it'll be the prototype version from the response. The idea behind this hello message is just to make sure that the server and the client are talking the same protocol type, which we're writing it, so it's going to be compatible. But the idea being, if we upgrade the protocol in the future, if the protocols change and they're not compatible, we can handle that. The idea is that requests will come from the user and responses will go to the user from the server, right? So when we connect a client, the client will send a hello package, and we're going to read that in as a hello request, and then we'll send the hello response. And if these two things match, the client decides that it can go forward and continue. And again, this is all server-side code. We'll handle writing the client towards the end of the project. So we are in the finite state machine, and we're currently going to handle the client state, right? So again, a finite state machine, we run logic based on what the current state is and some kind of logic. So we're gonna cast the client buffer in here. And again, the client buffer got filled during our read. We read right into the buffer. We're going to cast the buffer into a header type, and then we're gonna do some logic based on what data is in that header. So let's go try that out right now. Okay, so I've written some code here that converts the client buffer, which is just a char star, as a buffer for arbitrary data, into the header type of the database protocol, which is defined here, which again is just the type and the number of elements in that protocol, or in that packet. What we're going to do is we have to do our traditional unpack from network endianness to host endianness, and again, that type is a long, so it's 32 bytes. 32 bits, and then the length is short, and again, the length is just the number of sub-elements. So again, the idea here is we're in a finite state machine, so we're going to use the current state to determine what we do. So the current state of the client it's in state hello, which for my definition is going to mean we're waiting on a message hello request. So if we read in the data from the user and cast it to that header type and check that the type is a message hello request. If it's not that type, or the number of sub elements is not equal to 1, which means that there only should be 1 element in the packet when we get the hello message, then we did not get a message hello in the hello state, and we have to send an error message. Otherwise, if we did pass this, it means that it sent the right data. Now we have to read and see what is the data beneath that request, right? And or beneath that header. And underneath that header is going to be just, you go to the header element +1, and you get the address of that. We're going to cast that to a hello type. And then we again have to unpack the underlying, frame, which is going to be this type here. So the hello request is going to be the name of the structure. And all it's going to have is a protocol version. We have to, again, unpack that from network to host endianness. And we're just going to check to see, is the packet from the client reflecting that they are talking protocol version protover, and protover is going to be 100 for us. We can update this as the protocol expands. We can do semantic versioning to figure out if they are compatible or incompatible. But we'll say that they need to be the exact same version for this tutorial, right? So hello proto, if it's not the protocol version, we'll save a protocol mismatch and then send the error. Otherwise, if we've gotten a hello request, if we've gotten the protocol to be the right version, then we'll update the state to be state message. And in state message, what we're going to do is we're going to handle, okay, now that we've said hello to the client, we are expecting them to send us one of the data requests, right? So it's either going to be a employee list, employee add, or employee delete. So we can check for either of these three and then send the response after. So what we're going to do in the rest of this lesson is actually build out the client to do this hello exchange. And again, there's a reason that I'm doing all these definitions in a common.h file. When you're defining a protocol, you want to make sure that all of the types are exactly the same, right? Because if they're not, if you have, protocol.h over here in the server and then protocol.h over there in the client, if they're not the same file, then if you make a change to one area of the protocol, it won't carry forward into the rest of the protocol, obviously, right? So what we're going to do is use this information here to begin working on the client, and then in the client, we'll actually execute that protocol version exchange, and we're going to upgrade our client to the hello message state, and then we'll implement hello message in the next lesson. But for now, let's actually write that client. Okay, and so here is the client code. Again, if you can tell by the pattern here, the code is pretty much the same as the rest of the client code we've been writing. We do the basic stuff. We create a socket. We connect that socket to a given IP address and host using the server info, same cookie cutter stuff. What we do after we make the connection, and if assuming we don't fail to connect, we call the send hello function. And the send hello function actually reaches into the types in our common.h. And again, that's all a shared structure here on the left. And it will reach in and create a database proto header T. Database proto header T will get cast from this character buffer. This is our area to write with, and we just treat it as a pointer to that thing. And then all we do is we specify the type of packet that we want to send. And again, based on the state machine we've created and the kind of the agreement we've made with our protocol, we know that at this point in the code, we are in the state hello, so we need to send it a hello message request. And it's also going to be type or a length of 1. And then we have to cast those from host Endianness to network Endianness, which is what we do with any data that we serialize on the network. And then we just write it to the buffer. We write it to the file descriptor, and we write it from that buffer. And then we server connected protocol v1, right? And we can prove that this works by looking at the output from the server, which is currently listening on port 8080. And we'll go ahead and run our dbcli. And we get no error here because we haven't programmed an error in yet. But you will see that there was no error messages that came in from the server. So it passed all of our checks, which is pretty cool. And then, we're able to see that we are able to implement a finite state machine with different protocol specifications and different types. So we can use this to begin to expand our program to not only handle the hello state, but also a message state. So in the next lesson, what we're going to do is we're going to implement the add employee functionality by creating an employee add type and then add that to our state machine and continue on with the program. So we'll see you guys in the next one. Again, if this is too much for you or you think it's going too fast, I guarantee you if you watch it again and actually get your hands dirty and start writing some code, it'll all make more sense. So we'll see you guys in the next one. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. So in the previous lesson, we got the server to a place where it was able to run the client as a finite state machine. So what all we're going to do now is begin to implement the individual states that the client is able to be in and then handle them on the server. So in the previous lesson, we began to work on, we didn't really finish up the exchange of the hello message. So we can confirm that the client and the server were speaking the same protocol version, right? So I've added a little bit of code to the client to go through this. Let me kind of talk through what I've added. To start, really simple code. I literally just copy and pasted this from the server into the main function of the client. This allows us to check for the add employee string that we'll get to in the next lesson. But for right now, a port argument where we specify a port number and a host argument. Again, if you did the 0 to hero C programming, all we're doing is using the get option loop to parse out options and then check them for or convert them to the right type, and then use the type that is cast to do logic and see if we got the right argument, right? So for example, if we take the port argument, which is a string, cast it to a number, and we put that into the port value, if port fails to get set, like if it's a bad value, which is a return value from A to I, we say, hey man, that's a bad port, we can't use that, return -1. And then same thing, if we get through this loop of checking all the arguments and host arg is still null, we need a place to connect to. So you must specify host with tag h and you throw a -1. Otherwise, if we get through all of this, all we say is that we connect out to the host argument and the port. So we've added that as opposed to argv1 and 2, a little more dynamic. You can make it, better code that way. And then we have also implemented an error checking scheme. So let me kind of talk through this. So before, it was just the send hello to FD function. The reason why that's a problem is that making these functions avoid, not avoid the word, a void singular, is a problem because you need to have a way of returning whether or not the function was or was not successful. So to do this, we're going to borrow from the common.h file. So we kind of have just a uniform error checking scheme so that there's a status error value and a status success value. And the general case will be if we get something that happens incorrectly, if we get a negative or error response from the server, we'll return -1, otherwise we'll return 0. And we've added that to our client. So now instead of send hello being a void function, it's an int function where if we get the response from the server and it's a message error, that means, hey, there was a protocol mismatch, close a file descriptor and return -1 so that we can tell the client to eventually actually leave. And we've closed it twice, so we can not do that twice. And then otherwise, if we are all good, we get through all the gates we want to hit, we say status success and we check for that, and that allows the program to move on to the next level. And then also, we didn't really finish specifying the protocol version in the previous example. I think that worked because of a slight memory bug, so I want to kind of go through the finished state of that. So when we send the hello message, right, we first specify at the top of the protocol the header, which is just a buffer, and we say, hey, by the way, hi, this is going to be a hello message, and there are 1 subcomponents to this. And then the subcomponent, the address of that is just the next element next to the header. So we say get the address of header 1 and then cast that to a hello request pointer. And again, all of the types we're going to share between the protocol are in this common.h file. And this is a hello request. And the hello request just takes a uint16t where we specify the protocol type. And the protocol version rather, and the protocol version is just a shared pound define. It's 100, right? And again, you could define that protocol version whatever you want. You could use semantic version. The update to the first one is a major release. First one to the second one is a minor release, and bug fixes are in the middle or at the end. So that's kind of up to you for that. But we specify within that protocol, like PDU, that packet data piece, that the protocol version is protocol version. And then we do the traditional network endianness. We have to take it from host endianness to network endianness for all of our elements. And then we write it on the wire, right? What are we writing? We're writing that buffer and how many bytes we're writing, the size of a protocol header plus the size of a hello request. Very simple. And then we wait for a response. So we will receive up to size of buff or 4096 bytes. And then we have to parse that out, right? So if we get the type from that response, we unpack it from network to host endianness, and we check to see, hey man, is that a message error? And if it is, that means we got a protocol mismatch. That's the agreement we made with the server in our server spec, right? If we don't agree in the first hello message, you and I can't speak the same language, so we close the FD and we quit. And we implemented that here in the server poll.c on the server. So really straightforward, right? We set up the read, and when we read from the client, we unpack their protocol version. And if the protocol version they specified does not equal the protocol version that we're speaking, we say, crap, protocol mismatch, and we reply with a hello error. And all the hello error is just a message error. You may not need to break this out into multiple functions given that all the errors are the same, but for the sake of code readability, it may make sense to have a reply hello error for all the different error states. So that's it, and now you can see when it runs, we have it running over here, and when I run the CLI, I can go like this, server connected protocol v1, and it runs. It gets upgraded to a state message, meaning it's expecting a request from the client to either add, list, or delete a user or an employee from our database. And then instead, just to prove that it works, we can actually go into the client, run a quick little sanity check, and we'll change the protocol version to, I don't know, 6969, wonderful. We'll take that, and then we'll make this will have an error, but it's still running in the background. This is just the server saying that it can't run twice on the same port. That's fine. But when I run the CLI over here, which is now the new compiled version, we get a protocol mismatch and a protocol mismatch on the right. So gotta put this back to protover. That is how we're going to implement the basic challenge and response system in our finite state machine. So the first one is, like we just described, a hello message response where I give you the protocol version I want to speak, you reply with yours, and we're good. Now that we've been upgraded to the state message state on the server side, this is where we're going to expect one of the following messages, right? We want to either get an add request, a list request, or a delete request. So in the next lesson, we're going to go ahead and implement the add request feature, basically in the exact same way. We're going to create a structure that has some data. We're going to send the data, parse it out. If it's valid data, we'll say, okay, cool. If it's invalid data, we'll send an error. So we'll see you in the next lesson where we do that. Hey guys, what is up? Welcome back to your next lesson in network code that does not suck. So in this lesson, we're kind of evolving the state machine that we're writing, right? And previously, we implemented the state that we're able to exchange between the client and the server, kind of a hello response process where we exchange the protocol version that we're speaking just to prove that the finite state machine works and we can exchange information with the server. So now we want to actually add functionality to the server to do our evil bidding, right? Like our employee addition or our list the employees or our delete the employees. So all we really need to do to begin this is to add the functionality in the CLI to send that data to the server, and then in the server, receive it, validate it, insert it into the database. Before you watch this video, please, I really recommend, to get the most amount of learning out of this course, out of this entire platform, please try to write this the way you think you would write it, based on the current system we have going. And then if you can't write it, please come watch this video, learn about how I did it, and eventually read the code that I'm going to give out at the end of this course. But for now, let's go into kind of the implementation. So previously we had our send hello message, right? Which is just construct a header from a buffer, add data to that buffer, set the protocol version, pack it for network endianness, write the data, receive new data, unpack it, and do some kind of logic. And here logic is simply, if we get an error, leave, otherwise move on. So that's pretty much it. So what we did is we added the ability to read from our loop where we read the arguments to the process. One of them is going to be an add argument, which will be that comma separated string where we can add the employee. If you remember from the Zero to Hero C programming course project, which I'm sure you did, looking at you, the way you add an employee to the database is you give it a comma separated name, address, and the number of hours they've worked, right? So that string that we're going to send across the wire will be added here. So if we set this, it gets put into the add argument pointer, which is just a null pointer that sits on the stack. And eventually we check if we're past the point where we've sent the hello and it passed. If we no longer have a null add argument, meaning it was set on the command line, we call this a new send employee function. And the send employee function literally just borrows all of the code from send hello. It's the same exact process. It's just now we are now sending, instead of a message hello, it's a message employee add request. And we have one subunit in the PDU. That subunit is going to be of type database proto employee add request. This is just going to be another PDU like sub element that contains that comma separated string we're going to send to the server. We can go into the .h file here, our common.h, and just show that literally all it is a 1024 byte buffer. I think this is fine because you're just using, ASCII encoded data. Eventually, you could compress this because it is ASCII and has enough or low enough entropy to compress. And in theory, you could break this out into like 3 separate fields where it's like you have the username, the address, and the hours. But I think this is fine for the purpose of this lesson. So once we get past that, do the exact same thing. We copy it into that buffer, and I'm working on a course called Defensive Programming where I'll talk about the major security vulnerabilities and pitfalls people run into when they code. But we're going to do a stir end copy, and the length will always be the length of the destination, never the length of the source. So you do this to avoid buffer overflows, which we'll talk about in that course. So here we have the header type, which is just, we're packing up the message for the wire, writing and receiving, unpack the receive function. And again, if we get a message error, we messed up and we probably put it in the improper format. Otherwise, we are good to go and we successfully added the employee. So that's literally it on the client side. We just prep the data to be sent, we send it, and we move on. Very good. Now in the server, things have changed only a little bit. So we'll go into the finite state machine area and we've added kind of a new section. So previously, if we got past the hello area, we upgraded the client to a state message. And that means that the state message is awaiting for an actual action. And here, if we get a message and the client is in the state message, meaning that we've passed the protocol checks, we'll check to see what the input type is of that packet. If the packet is a message employee add request, which we're going to send it, we'll handle that appropriately. So just like the previous ones, we'll look ahead of the header and extract data from that sub PDU. And we're going to say that we're going to add the employee data. And then what's cool about this project, and this is the reason that I wrote it this way, it shows that if you write good code that works and you write it in a way that it can be written on top of, if it's modular, you can just literally copy and paste or borrow code that you've previously written and incorporate it into future projects. So literally for this, I didn't have to add a ton of code to this function that we're going to call to add the employee to the database. And again, the parameters being, we pass it the header of the database so we can update the count of the employees. We have the pointer to the array of employees that are currently being tracked, and then the current data from our packet. Now, because we are doing a little bit of different managing of the pointers that we have, I have added a little bit of functionality to this, but effectively all we're doing is first we're just saying how many current people are in the database, not super important. Here we add some defensive measures. So in the previous course, we were a little more trusting of the input because it's all local. I didn't really care too much from a security standpoint. Now we're running a networked application. So I really can't trust that the user is sending properly formatted data, right? So here I'm checking to make sure, okay, we get the stir-toke result of this. If it's null, we have to say that we failed, and do the same thing for the three sub parts of the string. And also, if the A to I of hours, meaning it's not a valid string, is 0, or a valid int is 0, we have to handle that as well. And then this is kind of the only major change from the previous code base. First of all, this was happening in the main loop in the previous project, so now I'm just adding it here because it has to happen here. There really is no main loop that's going on that I can check this with. And then also, the way that our employee structure works, it's literally just a static, or it's not true, it's a dynamic array of employees. If I wanted to make it bigger, I need to reallocate. But when you reallocate anything, you need to save the returned pointer from reallocate because it's going to give you a new chunk of heap data. So all we're doing is we're saying, instead of a single pointer, it's a double pointer, and we have to save the result of realloc to that location. That's what's happening here. We save the result of the employee pointer that comes from realloc, and then we just take that pointer and we do all of our operations on it, right? We add to the employees of the current database index the name, the value from name, which came from stir-toke, and then same for address, and then same for hours. And again, defensive programming, we are always choosing the destination buffer size as our size parameter, as opposed to the source, because we do not trust the size of our source information. So if we get past all these checks and all these copies happen and don't crash, which they won't, we go to status success, and we check that in the finite state machine. So if this is successful, meaning that we have properly parsed data, we will output the file. And this is just us writing the file to disk. I'll go over a slight change I made to that function here. But if it didn't succeed successfully, we'll throw an error to the client. Otherwise, we say a success message. The output file function did change only a little bit. If you remember from the previous project, the function actually stopped right about here. So what we would do is we'd take all of the data that was currently in memory in host Endianness format, we'd pack it to network or disk Endianness, and then we'd write it to the disk. And we would, for every employee, unpack that and write it to the disk as well. Now what we have to do is repack that into host Endianness so that we don't have any Endianness issues with the database currently in memory. Because if we don't do that, well, I was realizing we have to do, after we write it, we have to repack it as well. So we'll do network to host Endianness, because we pack it to disk Endianness, write it, and then we have to unpack it. So I found that right on the spot there. Yeah, and then there we go. So I can kind of demo it real quick. It's pretty sweet. We'll do, let's see, do I have a active, go this. Yes, we'll do DB server. We'll use a new file. We'll run this, address start in use. So I can actually just go ahead and show you guys it working right now. So we'll go back to this. And so currently I have some stuff in the server, but if I go and I run this guy with our new string here, I could say, DB CLI, port, host, and we're going to add a guy named Bob who lives at 123 ASDF, and he's worked 100 hours so far. We hit enter. We'll see from our server running in the background, we do the hello handshake. We upgrade it to a state message. We add the employee, and now the database currently has 2 employees, and then we disconnect. And we have not implemented the list functionality yet, but I can show you the XXD that all of that good information is in here, right? So just like before, we have Bob 256 buffer, his address 256 buffer, and then the number of hours 100, which is hex 64 that he's worked, and then the next blob begins. So yeah, that's the add functionality. Please, please, please don't just watch this and say, got it. Learning comes from struggle. Struggle comes from doing. So please go do this. And then in the next lesson, we're going to add the list and delete functionality. And yeah, see you guys there. Take care. Hey guys, what is up? Welcome back to your next lesson in network code that doesn't suck. In this video, we're going to talk about how to add the list feature to our project and kind of wrap up the project here. Again, really highly recommend, please, please, please follow along, do this project on your own. Don't watch the video until you do. And then once you do, if you either get stuck or you want to see how I did it, please then watch the video because I think it really helps to have someone else to bounce your ideas off of. But again, learning only comes from struggle and struggle comes from doing the project. So with that being said, let's talk about how I implemented the listing feature here. Just like anything else, we have to add the L option, which will just be an argument list flag that we specify to the program. And if we set it to in the command line, we get list equals true. And later on in the program, if the listing is true, if we ask the program to list, we'll run the list employees function. And the way I've designed this is in the list functionality, all it does is it says, hey, I would like to request a list, and there's no additional sub PDU. So it just sends that out to the server, and then we receive the response. The response is the message list response type, but the length is actually the number of employees that you're going to get back, right? So what we do is if we get the proper response type, we create room in our buffer for a single employee to go, and we iterate over that length, right? We say, let's say, for example, they give us 6 employees. So we'll go I equals 0 up to 6, and we're going to read one employee at a time, unpack the numerical values like the hours, and then just print the values, right? So it's going to send us an employee's name, an employee's address, an employee's hours. We unpack the hours and we print it. And then in the server, it's similarly simple, right? It's pretty straightforward. When we are in the finite state machine, we're checking, what we get past the state message. And then if we get the message employee list request, all we have to do is send them the employees. And what does that do? All that does is do kind of the same logic. So we construct a packet header and we tell them, hey, here is your list response. And and also the number of sub PDUs is going to be the header length, right? And again, obviously we're packing those for network Endianness. And then we send them that first. So we say, oh, hey, be prepared to receive N number of packets, right? So we receive that on the client side. And then after that, we create a pointer to our actual packet we're going to send, and we also have to extract the pointer from our employee pointer because that has to be, again, a writable pointer for the purposes of the previous video. But then we're doing the exact same thing on the server side. We literally stir end copy to our employee, the singular employee buffer, their name, their address, again, using the destination buffer as a size, and then we pack the hours for network Endianness. And then we write that one at a time. And that's really it, guys. Like at this point, with properly seeded poll looping and a well-designed finite state machine, you can add functionality to a server client architecture like really, really easy. It is not hard. So what we're going to do here is we're going to add a new client or a new employee. We'll say his name is P. Sherman. He lives at 42 Wallaby Way, and he has worked 40 hours this week. This guy's a stone cold killer. Boom. So we can add that to the employee database. See over here on the left, the server, it is happily happening. And then we'll do, instead of attack A, we'll invoke our new attack L functionality. So we'll do boom, like this. And we get a list of all the employees in the database using that kind of like send and receive functionality. So again, I hope you have enjoyed this course. I hope you can understand now that network code really isn't that hard. All you have to do is design applications in a way where you reduce the amount of complexity so that you can just write an application layer on top of very minimal networking code, exchange data back and forth between a client and a server, and kind of go from there. So in future courses, we will discuss threading, how to make this program thread safe. So right now, because it is multiplex synchronously, there really isn't a ton of race condition stuff that can happen in this program pending like a logic error and how the file descriptors are handled. But in theory, if you want to make this more efficient, you can use threads. But the problem with threading is that if multiple people have access to the same data at the same time, it kind of gets hairy. So we'll have a whole course on how to write successful, clean threading in C. And then also a lot of the code here, we kind of do some hand wavy stuff with the security of it, right? There's no authentication. I'm doing a lot of size of destination address. I want to have a whole other course called defensive coding where we kind of talk about like better practices to do this kind of stuff so that security isn't an afterthought in your code bases. But I hope you enjoyed this. If you did, please go check out the source code. Please build this yourself and implement additional features. Either at me on Twitter or hang out with me in the Discord and tell me what you built. See if you can build a delete function, if you can edit an employee based on some ID. Do something cool with this and kind of use this as like your test bed to learn new stuff. So I really appreciate it, guys. Thanks for hanging out.